Okay, so I have a cubic, the green thing over here, and I have a parabola. An interesting thing that you may notice, at least from this view, is that both this parabola touches and this cubic touches at this point. I'm just gonna like put this point over here, somewhere around there. Keep it somewhere here, close enough. Okay. So at this point, they both intersect. So the cool thing about that is, well then, how do I describe this? Okay, so not only does this intersect, right? This They also share a common slope. If you look away, to here, they both share a common slope. The slope of the parabola is the same as the slope of the cubic at that point. Looks close enough, right? Yeah. So if I bring my point around here, right? So what an interesting property is if I have myself the uh the cubic, right? And if I subtract the parabola from it, or if I equate them together, right? And I let the y values equal to one another, right? So in this case, if I just extend this a little bit, this is like a pretty messy parabola here. I just toyed around a little bit. And I have me my cubic, right? If I let the y values equal to one another, I get basically a polynomial in x. Not hard to figure out. So what am I doing with this? What am I doing with this is if I let all these x values equal to one another, and if I solve for it, I get to this point. Because that's the point of intersection. Not hard to figure out. But also an interesting thing is if I equate these two, and if I have like a complicated function where f of x subtracted by g of x, right? If I have that function, oh wait, sorry, no, f of x minus d is my parabola. Whoops. So both of these, if I subtract this by this, that's what this last thing is showing. The x cubed minus 2x subtracted by this top thing. What this does is it gets me a rather composite curve. That's what you can call it. This is also cubic, by the way. But an interesting thing is it has a double root at that x value. You see the x value, I mean, it looks off, obviously, but I'm just doing this like by eyeball. What it's meant to happen is, since that these both have the same curve, like the same gradient, at this point they have a double root, the subtraction of the two curves. It's kind of subtraction of ordinates in that sense, because if these both have the same y value, subtracting them gets you back to the x-axis. But what also happens is when you do subtraction or addition of ordinates, the slopes also get multiplied, or not multiplied, they get added or subtracted depending on your operation that you're doing. So since I'm subtracting these two, the slopes subtract as well. And so since they both have the same slope, they subtract one another, and so they have a slope of 0 while it touches the x-axis. What this means is that it's a double root at this point. So to summarize this theorem, if you want to call this, if I have two curves and they touch at one point, so if they have a common tangent, if I subtract one curve with another, and if I graph the resulting curve or function or relation, it will have a double root at that point of intersection, or that point where the tangents are equal. And that's what is shown up here. Okay, so this is the idea that I wanted to convey across. Now to apply this into actual question. One sec. Okay, yep. So my question is down here, right? So I have me a hyperbola, xy is equal to c squared, and it touches the circle, touches the circle at x minus 1 squared plus y squared is equal to 1 at point Q. So now, if I want to represent this, I have me this. I have me a hyperbola, and I have me a circle, and they touch at the point Q. So I'm gonna just call this, okay, I'm gonna just call this point Q. So rename point Q. Alrighty. So I mean the point Q. That's cool. Show this information on a sketch. I already did that. Forget the second part. We're up to the third part for now. Okay, so deduce that the equation, this thing, has a repeated real root at b is greater than 0, and the two non-real complex roots or whatever. Okay, don't worry about the latter part. So what I wanted to convey here is, now, how do we deduce this? Is through, again, the subtraction of ordinates, if you want to call it that. So I have me my circle, and I have me my hyperbola. If I subtract one from another, I will get like a composite curve. Not hard to figure out there. So from this, what can I do? What I can do is, this point will obviously be at the x-axis, but also their slopes are equal, so that means it will be a double root. And that's the thing that they're asking. Has a repeated real root at b is greater than 0. In this case, repeated double, it's at least a double root. Yeah? Okay, and two non-real complex roots, we'll worry about that later. Okay, so now, how do we get to this equation? Because we already have what? Y is equal to c squared, and we have x minus 1 squared plus y squared is equal to 1. That's what they said here. Up here above. Okay, that's cool. Okay, with this, right, I want them to be equated with one another in that sense, so they can sort of subtract, or like, we get to this sort of polynomial. So I will get y is equal to c squared over x, and I get y squared is equal to 1 minus x minus 1 squared. Okay, I have me a y and I have a y squared. It's easier to square this rather than square rooting this. So I'll just write y squared is equal to c to the 4th over x. And that's the same thing. So now, remember, these both touch, right? So that means they are equal to one another, right? And the solution, by equating this, we'll get the x value. Remember, if we equate these, that shows where they intersect, and that shows the x value of where they intersect. But that x value also is the double root of the equation that we'll get. So I get, that's x squared there. Okay, so I have a c to the 4 over x squared is equal to 1 minus x minus 1 squared. Okay, let's simplify this out a little bit. I'm going to bring this over to the other side. So I'll be getting c to the 4 over x squared plus x minus 1 squared is equal to 1. Okay, there's a fraction here. I don't like fractions, so let's just get a c to the 4 plus x squared times, so I'm multiplying everything by x squared, by the way. X minus 1 squared is equal to x squared. Well, what do we have here? The exact same thing. Haha, exact. Okay. So what this shows is, if I have me my composite function here, right? Now this is basically equating these two. So imagine what I do here is, if I get the x squared to the other side and let y is equal to all of this, what it shows is, at this point, at the same y value, this is a double root. And that's kind of what it's trying to convey up here. When you subtract two curves that intersect, you would just, if you equate two curves that just intersect, right, you just end up with the intersection with the x-axis. If you equate two curves that touch one another, so that means their tangents are common in that sense, then you end up with a multiple or double root, as shown here. This is like the key idea that the question was trying to test you on here. Yeah. Alrighty. See us.